Hello guys. Welcome to another video. We have collect coins in a tree. This has been previously asked by Uber and Lucid. Pretty nice companies. And actually, before solving this problem, we will want to look at the hints. So basically, you have a graph, right? And you have been given edges. So A, B shows that's a connection between what this node and this node, for example, right? Two different nodes, and these connections are bidirectional. And one thing we have is that the elements that are um, for the elements that are leaves, right? We have coins there, right? So leaves are elements with what maybe just one dependency in this tree. If you look at it, the element with no leaves, right? Sorry, I mean no children. That element is a leaf, right? And fortunately, in this question, we have coins being put at leaves, right? And there are two possible things we can do in this tree, right? We can collect all the coins at a distance of at most two from the current, or move any adjacent vertex. So move to any adjacent vertex in the tree, right? So you can probably be standing at two, for example, right? And at most, we can have two different moves, right? We can move to one and move to zero and collect this coin, or we can probably be standing at three, move to four and five, and also collect this coin, right? So that's a possibility. Or you can move from two to three or whatever, right? So the question is essentially asking us what's the minimum number of edges we will need to go through to collect all the coins and go back to the initial vertex, right? So we want to return to our initial vertex, but basically the question is more about like what the number of minimum edges that we have to traverse through. And instead of thinking of it in terms of the edges, you can think of it in terms of the nodes that are absolutely necessary, right? So for example, as I previously said, right, you can stand at two and then get to zero, and three also, and get to zero, and that will essentially be your answer, right? And also in this case, for example, right, you can start at zero because you have to at most two moves, right? So you can go from zero to one to three, collect this coin, zero to one to four, collect this coin, two to five to seven, and collect this coin, right? So very, very interesting question. And I think one thing that will help you with the intuition is that wherever you are standing, right, you should be standing beyond the parents, the necessary nodes. You are standing beyond the parent of a leaf which has basically a coin, right? So if you can see in this example, right, standing at two, why is two special? Because it's essentially the parent of what? A leaf with a coin. Same with three, same with zero, same with two, and so on and so forth. So we can use this intuition to our advantage. And I actually think that the hints are very helpful, right? So you look at the hints, it says all leaves that do not have a coin are redundant, right? So if you know in the premise that we are looking at two, at most two moves, right, then in the worst case, as I was previously saying, right, you can stand at a position where you are the parent to the parent of one with the coins. So those leaves with no coins in the first place, we can process them out, right? Like for example, here six, we can take six out. We are not going to use six, for example, right? And any subtree that depends on six. Now, obviously, six has subtrees, it wouldn't be a leaf. But for example, let's say something was connected to six and it was also not even a coin, right? Then we want to delete not just that, but also six, for example. And this is necessary, right? Because it is connected here. So hey, we do not touch that. So basically, we are going to use topological sorting. And let's look at the other hints, right? So we take care of redundant leaves, right? Because they do not have coins, and that's essentially what it's saying. Hint two, I want to remove the leaves that do not have coins on them. So the resulting tree will have a leaf, a coin on every leaf, right? That's what we want to work with. And then the remaining tree, remove each leaf node and the parent of and the parents from the tree, right? So remove the leaf node and the parents from the tree, and what will remain are the nodes in the tree that must be visited, right? That's what previously stated. And then you can calculate the number of edges left, right? You can keep a count, for example, and I'll show you guys keeping account for the number of nodes that we delete, right? So every node that we delete, we keep account, and then I'll use that to calculate for subtract that from the total number of what edges, and then we'll be able to get what the number of edges that we must pass through, or essentially the number of nodes that we must visit, right? So that's basically the core of the question, right? You want elements as a periodicity which are parent of what leaf nodes with coins, and those which are not having coins, right? We do not need, and they are not necessary, I guess. So what we want to do is first have a measure of what the number of nodes, right? That's n, and then we want to build a set of what, and basically our adjacency list, right? And I want to use sets because sets will make it easy to remove basically neighbors, right? So because like sets have like very good operations for what adding and removing elements, for example. So basically in our adjacency at every possible index, I want to put in an empty hash set, right? And after putting in our hashes, now we want to populate it with what the elements from edges, I mean, which is what into you, which is edge 0, and then same with V, right? Edge 1, come on. And then how are we approaching the problem? I actually didn't mention that, but this is going to be using topological sorting. In this case, we're not going to be using the n degrees, right? We can use the size of our sets that we are using, so that's a win for us. We don't need to keep account of n degrees, but because it's bi-directional, right? We add not only for v, like saying u is a neighbor of v, but also what same vice versa, right? So that's what I'm going to do here. So add u, right? Cool. So we've built our graph essentially, and now I want to keep account of what the total number of nodes. The total number of nodes is sorry, the total number of edges. And the total number of edges is going to be the number of nodes minus 1 times 2, right? And you can do the math yourself. You have 7 let me see, 1, 2, 3, 4, 5, 6, 7, right? And then you have basically, right. So total number of mind you, the total number of edges or connections, you have to think of this in the bi-directional sense, right? So we have essentially 7 edges, but we have essentially 14 connections, right? Because um, yeah, we have 14 connections, right? It's bi-directional. So 0 connects to 1, and also 1 connects to 0, right? So total is what 2 times n minus 1, right? And note that we have 8 nodes here. That's why it's n minus 1, for example, and would work here. So you have essentially 14 connections. So whenever we break a connection, so let's say we break a connection between 0 and 5, right? I delete that. And also break a connection between 5 and 6, I also want to delete that, essentially, right? So we will move that. And so the variable we use to keep count of the nodes we deleted is what's deleted. Cool. So in our first processing, we're going to deal with the edges that sorry, the nodes with which are those which are leaves but have no coins. And to do that, I want to create first a queue. All right, it's a new linked list. All right. And to it, we'll first add what the elements which fit our criteria, right? The leaves with no coins. Right. So how do you know it's a leaf? Basically, a leaf will have just one dependence, right? To only depend on its parents. It has no children, right? So if the adjacency of k, right? Now, if that set its size is equal to 1, then it means it depends on only one element, right? And it is a leaf. I want to check if what coins of k, if that is equal to 0, right? If it is equal to 0, we'll take q to add k, right? We add them to um, q, and then we do some processing, right? So while the q is not empty, right? What we want to do is what? basically take our current and it's q.pull, and then we get its parents, right? So it's parent is what basically the adjacency of the current, and it's the only element in there, and we can use iterator dot next in Java to get an element from our set, right? So when we do that, now we want to break the dependencies, right? So it's the adjacency of current. From that, we are going to remove parent, right? Now parent is no longer its neighbor, and then also, and then we can say, okay, we've now deleted one connection, right? So deleted plus plus, and then adjacency of what parent. Again, we remove its neighbor, and this neighbor in this case will be current, and again we increase deleted um, by one, right? And now, after you are doing that, you are done working with current, right? You can check if the parent, right, has just one dependency. Now, if the parent has just one dependency, then it is what is essentially not useful, right? Let's say 6 had an element 8 here, for example, and 8 had no coin. And if you already deleted 8 right now, if 6 just has one dependency, right, it's part of a subtree that is not necessary. So what we want to do is what to remove it also. So we want to check that if the adjacency of parent, if the size of that set, if the size of that set is equal to 1, right, then it qualifies, and we can add its parent to, set, sorry, our linked list, right, or our queue, and then do further processing on it, right. So at the end, we will be left with only the nodes where we have leaves at with coins, and everything else in between, right? Everything else in between that is necessary, and those are nodes will be potential candidates for the nodes that we must visit to be able to collect all the coins, essentially, right? So for that, now we want to add to our queue. Right now our queue is empty at this point. We want to add again to our queue now the elements which are leaves, and not just that they are leaves, but also what that it has a coin. So I'm just going to copy um, what we had initially and just change it here, right? So we're changing and we're adding only elements with what um, with sorry, with coins, right, as leaves first, and then we'll do processing on their neighbors. So in the processing, we have two levels of processing that I want to do, and I'm going to keep this in two. First, we want to deal with what's the leaf itself, right, and we want to deal with its parents, right. Think about it. The hint is telling us to deal with not only this one but the parents also, right. So we delete the leaf and then delete his parents, right. Awesome. So that's why we have two levels of that we are dealing with. So I'll just go and say wow, levels minus minus, if that is greater than 0, right, then it's fine. We can delete um you know what we have basically, where we delete the leaf and the parent. Okay, so we want to keep a size, right, of, or a count of the number of elements we already have in our queue at this point, right, which is what queue dot size. And from there, we want to have a while loop where we have size minus minus. Now, if that is greater than 0, right, now we can do processing not only for the child by its parents, right, and essentially we will be able to get at this point also, right. So with current q.pull, right, and then we want its parent, right. So it's a parent is what q. Sorry, it's and actually even before that, I want to check, right. I want to check if the adjacency of current, now if its size is equal to 0. If its size is equal to 0, then I want to continue. We don't want to do any further processing, right? But if it's not, then I need its parents like we did above also, right? So I can just copy this basically, right? So we get the parents, and now with that, basically we can just do this, right? We copy paste, right? Where we are removing the dependency on not just current, but what parent also, right? And then we are increasing our deleted count articles on. And if at some point our parent essentially becomes a leaf, right? We want to just add it to our queue, and then process it. But obviously, it's going to be processed in two levels, right? So it depends on if you are done deleting it, if it's parent is going to be added. So yeah, two levels, deleting a parent. And now with that, we can just now return what our total, right? The total number of connections basically, right? Because it's bi-directional, mind you, and the number of connections that we have was deleted, right? So this should work. Just don't want this video to be long. So topological sorting passes the first two tests. And there's an error. Oh no, oh no, oh no. I mean, is it oh, it says no such element. Okay, so I do want to check here also that if adjacency even has any element in the first place. If it does, then we want to do processing, right? Because if something has already been prior processing and is gotten again, it could lead to these kind of issues. So I'm just gonna um, okay, so basically it wasn't working because I think we had a case where this size was 0 and I was trying to look for parents. Um, so okay. Oh no, no, again, another error. Is it? Oh, it's actually giving the wrong answer. Okay. Ah, that might, that means I might have to do my formula. Okay, so 1 second. I see the issue, right? As I was previously saying, and I didn't follow on with that. But basically, let's say 6 had, another node 8, right? In our first treatment, we only not want to take care of the leaf by its subtree, right? Like its parents. If, for example, the parent also, after taking out the leaf, will become a leaf itself, right? Then it becomes redundant again. So we want to take care of it. And what I'm doing here is I'm checking if the size, right? We want to check if we can add the parent, but not only that, we also want to check that the parent is not a coin, because I think essentially the question doesn't guarantee that the coins are just at the coins are just at the leaves, right? So I was wrong about that. So if parent of coin is equal to 0, right? Sorry, is it coins? Oh, coins. Okay, cool. So sorry about that. Right, coins. I just saw that. Okay. Uh, did it work? Okay, so it worked for that one. In that case, let's see. So yeah, we passed essentially 79%, almost 80%. I What's the runtime, right? It's going to be O of n, right? Have O of n operations here, O of n operations here, O of n operation here, O of n operation here. Also, even though there are two while loops, just note that like each node will be touched at least, the relevant nodes will be touched at least once. So I hope you guys enjoyed the video, or got some benefit from it. I'll see you guys on the next one. Peace.